All right, grade eights. I hope you had a good Easter break. I know I enjoyed having a little bit of a break, getting some extra things or different things done than I normally would. Um, but we also had the Easter break a little later. So the good news is that you're going to be done relatively soon. So I hope you had a good break. We're going to continue to talk a little bit about linear relations, which was the stuff of the project before the Easter break. Who knows? Maybe after going through some of these, you'll find it a little easier and find the project easier for you to do if you haven't completed, or maybe you want to go back and fix some things. So here's an example of a linear relation. In math, relations are a very large topic or subject. Everything almost has a relation. If you can compare two quantities at all, then they have a relation. So it's a very, very broad concept in math. We're going to look at a more specific concept, particularly a linear relation. And the context we're using is pizza. Tony's Pizzeria sells medium pizzas for $9 each, and you can order extra toppings for $1 per pizza. So, maybe this is your basic cheese pizza. You want to throw some pepperoni on there, you have to pay an extra dollar. You want to throw some olives on there, cost you an extra dollars. If you want to throw onions on, it costs you another extra dollar. So that's what the extra topping concept's about. If we were to graph this scenario, and we had to decide how to graph it, first of all, we'd have to decide where our cost and our number of toppings go. So when you're figuring out which axis needs to be which, there's the x-axis, which is going to be your independent values. Your independent values and your dependent values are going to be your y-axis. When you're trying to decide which of those go where, you can think of it this way. The number of toppings that you have for your pizza will affect the cost of the pizza. And so that's why this is called the independent values and this one's the dependent, because one of these values is going to cause an effect on the other. The one that causes the effect is the independent value, and the value that is going to be changing because of the independent is going to be our y-axis. So our cost is going to be here and the number of toppings here. And if we look at the relation, the reason why it's linear is the points all sit on the same straight line. So if we were to look at this graph and try to figure it out, if we looked at the number of toppings being 0, that we found out was going to cost $9. As soon as we had one extra topping, that would add an extra dollar to the price of the pizza. So that's why it's now worth $10. 2 toppings, all of a sudden the pizza is going to be $9 plus $2 is going to be $11. So that's why the point here is at 2 and 11. 3 toppings is 3 and 12. So if we're thinking of these in ordered pairs, this ordered pair is 0, 8. This ordered pair would be 1, 10. This one would be 2, 11, and so on. And you'll see that they all sit in a line, and that's why it's called a linear relation. All right, another way to represent relations is something called a table of values. Here in this little thought bubble is a description or a way that you can see tables of values. When you set up table of values, they can be horizontal or they can be vertical. But whenever you set up table of values, you always want your x value to be either the top row or the first column, depending on whether you have a horizontal or vertical table of values. And the way this table of values works is just saying when x is 1, y is 5. When x is 2, y is 10. When x is 3, y is 15. When x is 4, y is 20. So it's, instead of a graph, it's just a table of numbers or values that describe the relationship between x and y. And I think if you look at this relationship, I think you'll notice that the pattern in this relationship is that y is always 5 times bigger than x. Because if you take 1 times 5, you get 5. 2 times 5, you get 10. 3 times 5, you get 15. 4 times 5, you get 20. And so that would be the relationship between x and y. And we could write the exact same relationship as a vertical table of values, which doesn't change anything because we still have x is 1, y is 5, x is 2, y is 10, x is 3, y is 15, x is 4, and y is 20. So this is another way to represent relations. All right, here's another example of how graphs, table of values, patterns, linear relations all match up. So this says the graph shows, so this graph here shows the number of triangles in relation to the figure number in the pattern. So for reading this graph, the first figure has 3 triangles, the second figure has 6 triangles, the third figure has 9 triangles, and the fourth figure has 12 triangles. It says describe the patterns you see in the graph. So one pattern that I notice on this graph is that every time we go an increase in the figure number by 1, we end up with 3 more triangles. So 1 more figure number, 3 more triangles. 1 more figure number, 3 more triangles. So there's this constant pattern here that forms this relation. If I have to draw this triangle pattern, then what I do is I recognize that the first figure number has 3 triangles. The second figure number has 6 triangles. The third figure number should have 9 triangles, and the fourth figure number should have 12, because those are the numbers that are on my graph. At the same time, if I'm making a table of values, because this is my x and this is my y, I need my figure number to be my x, my first column, and my number of triangles to be my y, or my second column. And so when I had one figure number, I had 3 triangles, which is right here. If I had my second figure number, I had 6 triangles. If I was at my third diagram or figure number, I have 9. And at my fourth, I have 12. And so there's my pattern written in a table of values. The last part to this question says, if the pattern continues, how many triangles are there in figure 99? Well, I'm starting to get a pattern recognizing here that the number of triangles is just always 3 times more than the figure number. So if I'm looking for the 99th picture or the 99th figure, then I would just take my 99 and times it by 3, and I would have 297 triangles. And no, I don't want to draw that out. But that's an example that connects linear relations, because this is a linear pattern, to graphs, to pictures, to tables of values. And all of that would be very useful for the project you had just before the Easter break. Here's another example that I'd like to go through. This one says the graph shows Nicole's rate of pay based on the number of hours she worked at her part-time job. So the number of hours she works affects the pay. So that's why the number of hours she works, the x-axis, and the pay is the y-axis. If we look at this pattern that's here, 1 hour worked is $10, 2 hours is $20, 3 hours is $30, and 4 hours worked is $40 worth of pay. It says describe any patterns you see in the graph. Well, that for me is a pattern right off the start, is that every time I work another hour or Nicole works another hour, she makes $10 more. And so when it asks what is Nicole's hourly rate of pay, because she is always getting $10 for every hour she works, that is her rate of pay, $10 per hour. Make a table of values from the graph. Well, if I'm trying to make a table of values, when I build up my table, this time it's horizontal, my first axis has to be my x-axis, so that has to be my time. So time, and then pay is my y-axis. If you work 0 hours, 0 pay, although that's not a point on the graph. But if you work 1 hour, or if Nicole works 1 hour, she makes $10. If she works 2 hours, she makes 20, 3 hours, $30. All of that sits in the table of values. Is it possible to have points between the ones in the graph? So in other words, can you have points somewhere like here? Could you work 1.5 hours? Well, I'm going to say that you could probably work 1.5 hours and get paid for 1.5 hours. However, I wouldn't think that you could work 1 hour and 3 minutes and get paid for that amount. So there could be some points in between these, but there wouldn't be it wouldn't be all filled in because we don't get paid by the minute or by the second, at least not that I've ever noticed before. And so maybe the answer here could be, yeah, we're only going to get paid by an hour. So if you work a half hour, you don't get paid. You have to work the full 2 hours. But it seems likely that you could get paid for a half hour's worth of work as well. So it is possible to have some points in between here, but it wouldn't be all filled in. So in other words, we couldn't work 3 minutes into the next hour and figure that out. Anyway, hopefully these examples help you get an understanding of linear relations, how to graph them, and table of values.